Hello there, and welcome. Today's webinar is the third in a series that I've been doing all about the rank operator. So to start with, I thought I'd just recap what I've discussed so far in that series. Now up there you can see a link to where you can watch it on Dyalog.tv. If you happen to be watching live now on Dyalog.tv, then Adam will paste this link into the chat. And he's also available for you if you want to ask any questions or give any comments, and he'll be able to forward those to me to respond. Or he'll respond himself. If it's small, he does that as well. Anyway, so what did we talk about? Well, the first webinar was just an introduction, and we looked at the basic syntax. So applying a monadic function to specified subarrays of some specified rank. Being careful, because if you use a function which acts on trailing on the last axis, then you'll have no effect, and we'll see some more of that today. We also looked at applying functions dyadically. This allowed us to kind of match up frames, collections of cells, in a way that kind of extends the idea of scalar extension even further. This kind of cell or frame extension. Very useful. And we also looked at the ambivalent case, which, while not as widely used, I'd say, does allow you to create some quite versatile functions. Now, I've expressed these constructs this way by parenthesizing the derived function. And I think for teaching purposes and sometimes in code, this gives a bit of extra clarity about which part is the function and which part are the arguments. But some people, some people like to write these using the right tack function to separate the operands, the rank, from the argument array. This is perfectly valid as well. You can also separate a function from arguments by assigning it to a name first. I thought I'd just mention this. But all of these things have the same common thread, which is this format. And we've used this kind of look, for expressing these types of functions when talking about the rank operator. I just thought I'd make it clearer how all that fits together. Then, so that was the first webinar, Introduction to the Rank Operator. In the second one, another link up here, we looked at more advanced uses of the rank operator, including negative rank as a kind of rank specification which is relative to the rank of the whole array, and also using multiple rank applications on a function, which allows you to have even finer control when sort of combining collections of cells in some way, especially dyadically. Really control these loops while keeping your arrays flat. Nice. Today, we're going to be looking at the rank operator and its relationship to dyadic transpose, especially in contrast to a couple of constructs which use the bracket axis operator construct thingy. I think, as I've mentioned before, bracket axis, despite being in APL quite early on, it's not a standard operator. It doesn't follow the same syntax as rank and each reductions, for example, and also it's kind of ad hoc. It's defined differently depending on which function you're using it with. This has caused problems for people who try to derive some general regular operator that would do the same thing. We're going to look at a couple of functions which get kind of towards that, but only for two specific functions we look at, which are going to be enclose and Ravel. And as we go through this as well, eventually we're going to get to a kind of general array algorithm, a kind of method for applying leading axis functions along not just subarrays specified by rank, but also subarrays along any axis that you want to specify. That's not super clear right now. Hopefully, with examples, it'll get much clearer. So let's look at the first example then. The Ravel function, take all of your elements, some array, and kind of lay them out just into a single vector. And you can also think of this as merging all of your axes into one single axis whose length is the product of the size, the length of each of your individual axes. But not only can you, merge all the axes like that by default, you can also specify some collection of consecutive axes. So in this example, it's 2, 3, and merge those axes, merge data along those axes. And when you think about the arrays in terms of their shapes, then it's quite clear what's going on here. So in this example, we have our 3D array, which has dimensions 3 by 2 by 4. And what we end up with is merging the last two axes, axes 2 and 3. The result is a single 3 by 8 matrix. But if you kind of go back and you squint a bit and think about the input array versus the output array, you can also see how that can be thought of as just raveling each of the matrices. And certainly you can write it this way now as well. So I want to ravel my rank 2 subarrays. And as you can see, you get an identical transformation in this case. So merging trailing axes is quite easy with rank. Maybe you're seeing where I'm going with this. It starts to get a little hairier, a little bit more difficult when we want to merge leading axes. Obviously, this construct is fairly neat looking, and again, in terms of the shapes, it's quite clear what's going on. And even when I look at this representation, this flat representation of my 3D array, I can kind of think, I want to just squeeze the planes together so that they're joined. I just want to remove, if I had a text editor, I'd just delete the gaps there. But how do we do this by actually manipulating the arrays? Actually transforming the data in the arrays? Well, again, we want to sort of ravel two-dimensional subarrays so that those two axes become one. But we're looking to merge the first two leading axes. It means to do it with rank, we have to move those axes to the end of the shape. And this is where dyadic transpose comes in. Dyadic transpose is a little bit off-putting for a beginner. I know I didn't find it very easy to understand first, especially for high rank arrays, which is really most of its use. In terms of the shape, start to grasp it a bit more. It still gets hard to think about how the data shuffles around until you actually play with it, but I like to think of it as a reorder axis function. And so, that in mind, I've kind of developed a bit of a mantra by the end of this webinar you'll be sick of, and it's the idea that, okay, so I've got my leading 2, length 3 and 2 axes, and I want to move those to the end. And the left argument to dyadic transpose tells me where each axis is going to end up. So the first axis will become the second axis will become the third axis will become the first. So that's 2, 3, 1 transpose. Right, I'm gonna do this a lot for the rest of today. So yeah, bear with me here. It's gonna be a lot of that type of thing. After we've done the transformation, you can hopefully now see how the data that we were interested in, which is sort of lined up along our first 2 axes, has now been sort of collected together into matrices, which we can then use Ravel rank 2 as before to merge those 2 axes before finally transposing again to get the same relative axis order that we had in the beginning. Now, for quite simple or for individual transformations like this, where I know exactly what the data is, I know exactly what transformation is I'm trying to do in this way, then these types of expressions aren't too bad to come up with, and certainly it's probably quite good practice if you're trying to get to grips with the rank operator and dyadic transpose to try these sorts of things out. See if you can deduce the left argument to dyadic transpose yourself. But what about a general, just write a defun which does the same thing as Ravel with Axis, but just using rank and transpose? Well, it gets a little bit hairy, a little bit involved. This topic did come up in the Dyalog forums a while ago, and this expression also came out of it, although you'll notice that this expression is only covering, or basically a third of the functionality of Ravel with Axis, and that's consecutive leading axes. So, okay, trailing axes, we just saw a minute ago, is actually trivial. It's just comma with rank, Ravel with rank. The one thing we are missing is you can also specify consecutive axes that lie in the middle of the shape. So if you had a rank 4 array, you could combine axes 2 and 3. To do that, it gets a little bit more complicated in terms of the code, but the process, the idea is the same. And we're going to be following this a bit further now. So get the axes you're interested in and move them to the end. Then use Ravel with rank to merge the axes, and then do some other transpose to move the axes back. Right, so in APL, for Ravel specifically, it looks like this. I will come back to this in a moment, so I won't go into loads of detail. Okay, so now I'm going to pivot a little bit. Instead of talking about merging axes, we're going to look at enclosing subarrays along specified axes. And to start with, I'm going to have a sort of half moan about the split function. Nothing really wrong with it, except that it encloses vectors along the last axis by default. You can give it axis specification. So here I'm sort of highlighting to show you where the data is, how that gets enclosed together. This sort of down the planes we're going to collect vectors. If we specify the second axis, then we'll enclose vectors down each column. And finally, well, third axis is the default for a rank 3 array. And as I've stated in I think the first webinar we talked about this, if you have a last axis primitive, it means that just applying rank is useless. It doesn't really do anything. In fact, I find it slightly strange that when you have the first and last axis versions, like /bar and /, the axis specification does the same thing on both, even though their defaults are opposite ends. Of course, the thing about split, even though it was in APL before the rank operator, so they might not have thought of it this way at the time, actually we can just define it now as Enclose-rank 1. And now it becomes obvious why the extra applications of rank don't do anything. Enclose-rank 1, rank anything is just rank 1. So where we're going from here is directly related to what Adam talked about at the end of his webinar, part 5 of language features in Dyalog version 18. In there is an extension to Mix-with-Axis, but he also discusses how that same construct can be rephrased as just mix on its own, which puts your the extra axes it inserts, puts them at the end, I believe. Please correct me if I'm wrong. And then you can use Dyadic-Transpose afterwards, and you have even more control because you can rearrange the axes any way you want. Whereas with the extension, just Mix-with-Axis, you specify the axes, specify certain axes to go one way or the other, and then it fills in the rest. So where Adam's webinar was discussing taking some nested array and increasing its rank, sacrificing some depth, here we're going to look at doing sort of the opposite. We're going to take some high rank flatter arrays and turn them into lower rank, more nested arrays by enclosing some specific subarrays. So to start with, let's continue on with split. On the first axis, so have a think now, how would you rephrase this using rank and Dyadic-Transpose? Well, what we're going to do is we're going to substitute split with Enclose-rank 1, enclosing vectors. And then the transpose, well, the vectors we want to enclose currently lie on the first axis, but Enclose-rank 1 acts on the last axis, so we have to move it to the end. Okay, so the procedure again. First axis becomes the third, second axis becomes the first, third axis becomes the second, so that's a 3, 1, 2 transpose. Then just enclose those rows. Okay, another one. Have a little think. You can do the same thing. In fact, I'll just go for it. We want to move, we're going to enclose vectors from the middle axis, so that's the one we need to move to the end. So the first axis, keep it where it is in position 1. Second axis becomes the third, and the third axis becomes the second, so that's a 1, 3, 2 transpose. Okay, and one more time for the people at the back. Yeah, okay, you don't have to do anything in this case, it's literally just the default for split, and as we said, we just substitute for Enclose-rank 1. Now, so split can enclose vectors along a specified axis, but there's another primitive function that can enclose vectors called enclose. And it has the added benefit that it's kind of leading axis oriented. It encloses the whole array by default. So applications with rank allow you to specify subarrays in that consistent way. Of course, you can give enclose an axis specification, but if you give it a single axis, it ends up identical to split. Does all the same stuff. Although it has the added bonus that you can specify multiple axes. So it'll enclose higher rank subarrays along those two axes. So again, alright, let's have a look. How can we rephrase this in terms of rank and a dyadic transpose? So this time, instead of enclosing vectors, we're enclosing matrices. So it's going to be enclose-rank 2. And here we've specified the first two axes. So we have to do that thing again and move the leading axes to the end. Right, so the first axis will become the second axis becomes the third, and the third becomes the first. That's a 2, 3, 1 transpose, and enclose rank 2. Right. Let's look at the trailing axis. Yeah, okay. It's you don't have to do anything. It's just enclose rank 2 now, because the axes we care about are already the trailing axes in this case. Now enclose, so Ravel with axis, you have to specify consecutive axes. Otherwise, it's like, what do we do with the axes afterwards? We want to put them back, but if they're not consecutive, we put them to the end or to the beginning or which part of the middle. So you can't specify non-consecutive axes with Ravel to merge axes, but you can with Enclose specify non-consecutive axes. How does this work? Have a little think, but the process is the same. Right, so we want to enclose data that lies along the first and third axes. We want to keep the relative order. So first axis, again, it's enclosing matrices, enclose rank 2. First axis becomes the second becomes the first, and the third stays as it is. So that's a 2, 1, 3 transpose. And enclose rank 2. And not only can you have non-consecutive axes, you can also change their order with Enclose-with-Axis. So same sort of thing, except now we want to flip the relative order of those axes. So first axis will now become the third. Second becomes the first again, and the third becomes the second. So that's a 3, 1, 2 transpose. Hopefully it's becoming really clear now how this is just another way to get to grips with thinking about these constructs, even if you don't feel like these are any easier to read than bracket axis looks quite neat. I almost start to consider it a syntactic sugar these days after having done all of this stuff. Of course, you can enclose and specify all 3 axes, but that's just no transpose, just enclose. But you can specify all of your axes in a different order if you want. Which leads me to, is there a good way to get from, is there like a expression we can come up with to get from axes specified in bracket axis terms to a left argument to dyadic transpose? Leading question, of course there is. And actually this brings up a fairly interesting point. So in bracket axis, your axis specification has the number, the value referring to which axis, and the relative positions tell you the relative positions that they want to be in. Whereas with the left argument to dyadic transpose, it's the positions which specify which axis it is, and it's the numbers which tell you where they'll end up. So the relationship there, okay, last hint, we're going from values to relative positions. The relationship is an upgrade. Right, so if we do an upgrade, it tells us the indices, if they were sorted, happens to be positions we want them to end up in. So that's sort of leading us towards this more general function we can write, and sort of gives us another perspective on these constructs and their relationship. If you want more practice by hand, then just use Deafen's PMAT and go ahead and do this. I think if you're starting out, want to get to grips with dyadic transpose, this exercise isn't too bad. So yeah, finally now we're looking at these functions, right? So this is Enclose-with-Axis expressed in terms of rank and transpose and all the intermediate transformations that we need. So especially this middle line I want to highlight, where we can specify some number of axes, doesn't have to be all of them, see, and this expression sort of just pushes the ones we've specified to the end, and then the grade tells us, converts the axis specification, as in bracket axis style, into left argument to dyadic transpose. And then there's not much to it with enclosed axes because that doesn't need to do any reordering. In contrast, the merge axes function, basically identical, except at the end, if we've specified leading axes or axes in the middle, we want to restore the relative order at the end. I think my main, again, the sort of caveat with this is this assumes much like Ravel with Axis, this assumes that your specified axes are consecutive. Of course, if you want, you could remove the restoration part. You have a function which will let you merge any two axes, basically in any order, but they will always end up at the end of the array. Do with that what you will. I mean, here's the rub really. So, well, we have this kind of method, which is really a way of thinking about these array transformations more than like a practical tool you'll use, because I think, as we mentioned before in various webinars, to get the most out of the rank operator, really you want to be, from the get-go, from the beginning, arranging your data in a way that works with it. This is kind of, apart from being an interesting sort of exploration, comparing rank, transpose, and the bracket axis thing, it's kind of this general purpose algorithm for applying your leading axis function to any subarray. That's fine, but you probably want to be arranging your data in a better way in the first place. So what we've developed here is a sort of broad strokes general purpose array algorithm. I want to apply this function to data along these axes that I've specified, and the way you can do this with any user-defined leading axis function and the rank operator, right, is to move your axes of interest to the end using dyadic transpose, apply your function using rank, that number of trailing axes now, and then if you need to, move them back how they were before. As opposed to, I suppose, writing your function with each primitive that would utilize it with a specific bracket axis thing. I suppose with this you can have a single a single leading axis function that you can apply by itself using, or to the whole array, work on major cells or something, apply using rank to apply on subarrays, or use this to apply on subarrays of different specified, not just the trailing axis, but any specified axis. Now, there's also a version of this that will work as well in APLs don't have rank. The trick here is basically, instead of applying with rank, we're going to apply a function with each, and we're going to utilize the implicit transpose that Enclose-with-Axis has, fix the result. But of course, this version using rank will give you better performance generally, because we're not creating some big nested array. Immediate. So, today we looked at, so I'm just going to begin to summarize now. Today we looked at increasing nesting on trailing axes that are specified using rank or on the whole array. Adam, in his webinar that I mentioned earlier, talked about decreasing nesting. Default behavior is fine, it doesn't require rank. We looked at merging data along trailing axes, and then with all of these in combination with Dyadic-Transpose, you can get that ability to manipulate array structure in all these different ways. Now, of course, this is not in any way an argument to substitute bracket axes or anything like that. When something's mnemonic, when something works, expresses what you're after, then obviously that's what you want. But these sort of exercises, this way of thinking is good practicing array manipulation. If you can master this, then you're getting really good at array-oriented programming, array programming. So this is just to summarize what's been discussed in all three webinars. Basically, if you're learning the rank operator, just know that there's basically a fairly finite list of things to master before you can say that you've basically got it, I think. What's the main difference being all of these ones at the top are derived functions, whereas the bottom is this kind of expression, which its usefulness to you will depend massively on what f is. I will. Okay. Questions so far. So yeah, that's all I really wanted to say about the rank operator and Dyadic-Transpose. Hopefully that annoying mantra method gets a bit monotonous after a while. Can help people to get comfortable with Dyadic-Transpose. Otherwise, next week, I believe the British APL Association again will be having another one of their open sessions on Zoom. That's fun, come hang out, talk APL stuff. Next Thursday, same time. Right, okay, a little bit of clarification, I think. Yeah, so here's a question. Some time ago, I think I said something that suggested to Ellis, who's giving the question, I should change what I meant by cell. Today you spoke about collection of cells. And what is a cell and what is an element? Oh my god. Alright, so this is the curse of array nomenclature, array terminology. It's like not super consistent across things, and then we have the annoying thing about nested arrays. So can you see this okay? I'll make it a bit bigger. I don't have like to hand the definitive answer of what is an element, or what I guess are called items, elements, and cells. Now, cells, I personally, and throughout all these webinars, I think I've tried to be quite consistent. And a cell is any, in fact, oh, let me give you the APL wiki definition as well. It's basically a cell is any subarray rank of some specified rank defined along the trailing axes, basically. So the bracket axis construct allows you to specify subarrays along these axes. In my selecting from arrays webinar, I have this kind of cube 3D model of a 3D array or even a 4D array that kind of demonstrates this distinction a bit clearer. Whereas cells are very much, and like I said, let me find. Oh yeah, there it is. On the APL wiki, we have a whole page called cells, and it, in particular, leading axis theory, which is this sort of modern APL, modern array language way of thinking of arrays that leads to the rank operator and such. And so, yeah, so a single index along some number of leading axes and the whole of each trailing axis. So this is the cells, and and cells very much is talking about high-dimensional arrays like this. Like, it doesn't matter if they're nested or not. The zero cells are your scalars, but if you have a nested array, those zero cell scalars could be unpacked into what's inside. And the debate, in terms of terminology, I say debate, moderate, tepid discussion is, are elements the zero cells themselves, right? So in iota 4.4, maybe iota Enclose-2.3, right? Is the zero cell, if you look at the shape tilde, right? Is that the element, or is the element the array which is inside when you disclose that? Again, so elements, I can't say I'm an authority enough to say, this is what an element is, this is what an element is not. I think the word is used kind of interchangeably for things, but cells definitely refers to just, so this would be a cell, right? This would be a zero cell of that array. You don't unpack the nested parts. Items, again, I feel like items is on the other side of cells. Maybe I should arrange it like that. An item could either be the zero cell or it could be the array inside the zero cell. And of course, for flat arrays, we have that caveat, which is that the array inside a zero cell is the zero cell itself. This is the floating scalars thing. So J has their explicit boxes, which probably changes the terminology a bit. Anyway, hopefully that's enough for you to at least have an idea of what those things mean. Also been asked to check out sigapl.org for an event on October 12th. APL Bay Area Users Group. Is this going online as well, is it? Aha, the URL for this virtual meeting will be announced later, so please check back here. And okay, so now I'm gonna wrap up on cells, and then we'll talk about events. So, oops, sorry, we're looking at my the cells. Right. In general, see the APL wiki. Alright, so look for cells to find out what cells are. Turns out there is a page on elements. And whoever's written this, presumably Marshall, has tried to make it clear what the APL wiki's usage of element means versus what it might be used in flat array languages or the contents of a box in a boxed array. Okay, and then yeah, I think that's that for terminology. Let's talk events in order. Oops. In order. So next week, next Thursday, same time, Zoom meeting with the British APL Association. Open session, general discussion. I haven't heard of a specific topic this time. Then, 4 days later, Monday, October 12th, is the APL Bay Area's users group, California, are having a meeting. Basically need to check back here, huh? 10 a.m. I didn't read time zones. The one on the west coast, presumably. So you can use Google to figure that out. URL to be determined. And lastly, so this is the last Dyalog webinar for a little while. Before I figure out what content to put in what format in the future, including probably some more pre-recorded shorter videos on various topics. So you can keep an eye on the dyalog.com events page or dates for your diary page to see future ones. But before then is Dyalog 20 online, the Dyalog 2020 user meeting on Monday the 9th, Tuesday the 10th of November, so this is next month. And you can register now on the Dyalog website. I'm just having a little pause to see if any more messages coming. Everyone's typing. It's a long one. Stopped. I'm going to take that as an indication to end now. Hopefully people watching in the future will see the first part as concise enough to get what they want out of it, and people listening now will have heard of all the events that are happening and a little bit extra array terminology, which, as I said, don't yeah, it's good to try and be consistent, but don't get too hung up on it because the APL community, the array language community, is not very consistent with their usage. Okay, I think that's it. Thanks again very much for watching, and we'll see you in the future. Alright, goodbye.